All right. Okay, perfect. Well, thanks everyone. Welcome. I hope to be explaining to you a little bit more about who I am, what I'm doing, what I've done before, and I hope you walk away with a little bit more knowledge about who I am. So I'll actually structure this in a couple of parts. The first part will be just about me a little bit, also a little about what I've done before and what like the things I've done in previous years. And after that, 15 minutes, I will talk about what I'm doing here as part of the project. So yeah, who am I? About Bas. My education. I went to this beautiful monastery here. It's an old monastery. It's my high school, and I did a very physics and biology oriented profile. Also joined the sailing club there. So I'm a sailing instructor now at that sailing club, and I did a final project on the Higgs boson. So if you watch the news, the Mr. Higgs actually died last Monday, but it was a really interesting project on particle physics. Went to DELFT for a bachelor in mechanical engineering, followed a minor on technology-based entrepreneurship in the third year, and I developed a startup with a couple of other students, made the product, the concept, marketing, finance, everything. It was a really interesting minor. And my thesis was on non-intrusive settling velocity measurement. That's a lot of words, basically just means that you're measuring the settling velocity of objects in mud, because you cannot see them, you cannot touch them because you influence the experiments. You have to somehow non-intrusively measure their falling velocity. That was a really interesting project, a lot of electro stuff. I figured it was going a bit quickly with my studies, so I was like, okay, I'll do a gap year, full-time gap year. Became part of the TU Delft Hydromotion team. I'll explain a little bit more about that in a bit, but I was chief people and I managed this team full-time for a year. I continued with my master at Delft, which I'm still doing, mechanical engineering, but specifically the track multi-machine engineering. I took 71 credits the first year because I was like, well, if I do 60, I'll be sitting on my ass all week. So took some extra courses on machine learning, for example, programming drones to do obstacle avoidance with a single camera. So if you know anything about depth perception, it's really hard to do that with one camera. Also, evolutionary algorithms and intelligent vehicles, a lot of interesting stuff. Also did a research project in September for 3 months, and also talk about it a little bit more in a bit as well. So yeah, just very quickly, so you get to know me a little bit. My hobbies: I go running 3 times a week. I go to the gym 4 times a week. That's my basic schedule.
That's a lie.
That is not a lie. And I also add cycling and hiking.
Being aware that I'm recording on YouTube.
So yeah, I also add cycling and hiking to that. So 7 times a week is the minimum, 8 more on average. And as I said, I'm also a sailing instructor. I'm also a technical advisory board member for Hydromotion team. As an alumni, I give feedback and tips to the new teams after my like last year and this year and next year's to come. Basically overlooking board of the technical part of the team. Also a big fan of watching sports. Formula 1 for sure, cycling also for sure, and also ice skating, running, Olympics. I watch it all. So yeah, I've talked about it a little bit. Hydromotion, what is it? You've seen some of the backgrounds. So Hydromotion is a student team from Delft. And I became part of this team in 2021. And essentially it's a team of about 25 students, new students each year, that design, produce, test, and race a hydrogen-powered boat. It was previously the solar boat team, because they made boats with solar deck on it, starting in 2005. But in 2020, so the year before us, they stepped over to hydrogen, because, well, solar panels are just not going to be the thing for making the shipping industry sustainable. There's no future in that. So we actually continued with this trend. We made a completely new boat with a new hydrogen system in it. It's also a hydrofoiling boat, has a couple of hydrofoils under it. And we continued this trend. You see some of the pictures in the background. This was in Monaco, actually, where the race was. And the mission of this team is basically to inspire the maritime industry to go sustainable. Because we see a lot of companies that are not willing to make the step towards sustainable energy sources because they're looking at each other, looking at governments, and everybody's waiting on each other. Nobody's wanted to take that leap into the sustainable energy sources. And we try to collaborate with these companies to basically show and demonstrate the feasibility of hydrogen, especially hydrogen in shipping. And we show, okay, well, if we can do it as a team of 25 students, surely all the companies can do it well as well. And we say to them, well, if you help us sponsor us with a little bit of money, that's nothing compared to starting up your own R&D development on this. We can give you all of this knowledge about hydrogen, and we can help you make this step towards sustainable shipping. And we see actually a couple of our partners already implementing our technologies, our ideas into their boats and ships, trying to make them more sustainable. So that's really interesting because that's basically our goal. I guess the second goal would be to educate people in the team, so people like me, students, to work, more in practice instead of theory. So yeah, what was my role in this whole team? I was Chief Ecodynamics, also abbreviated as VD. I managed the VD department, basically all the moving parts of the boat. You can think of steering system, driveline, motor, everything. But what people do not often realize is that it's also a hydrofoiling boat. So the foils, the wings that go under the boat, that basically hoist the hull out of the water, are also part of our department. And also the struts, basically the things that connect our foils underwater to our boat, which is 1.5 meters above that. And as chief, I actually also did the partnerships and suppliers of our department, which was actually a lot of fun. A lot of calling, a lot of mailing, but it was a very good experience for me. So yeah, to give you a little bit of an expression of our team, we see a couple of pictures here. Top left, you see actually the bottom of our strut with propeller, the hydrofoil needed, and the actuation system, which helps change the angle of attack to increase or decrease your lift. You see there the boat almost foiling. The whole goal of hydrofoiling is basically to hoist your hull out of the water, replacing hydrodynamic drag with aerodynamic drag, which is actually a lot less, which makes it much more efficient in sailing. You see here the driveline with the gears, which are normally submerged in water, in oil, I mean. The christening of our boat with a Dutch politician who was really advocating for sustainability, hitting a champagne bottle against our hull. And our hydrofoils, which we made, they're completely made out of carbon. If you know anything about carbon production, you know that it's a lot of work. It took us 4 weeks to lay 80 layers of carbon in each, everything by hand. And there's actually also 3D printed titanium parts inside of them embedded into them. That was 4 weeks of hard work, but a really cool project. So yeah, about research, I mentioned a research project that I did as part of my master in September. I'm actually going to talk a little bit more about this now. So it was a 3-month research project. It's part of my curriculum, and it's basically like a small version of a thesis. My subject was multimodal dark vessel detection. To go a little bit more into what dark vessels are, they're essentially boats that turn off their AIS being automatic identification system, which is a transmitter that transmits information about location, speed, heading, ship details, basically in the open. And other ships can capture the signal, and it's used for stuff like collision avoidance and like alarms, raising alarms when 2 ships come close to each other. So it's really important, and it's actually mandatory to have this enabled on your ship. But some vessels try to turn this off, mostly to hide their location, and they're often involved in illegal actions, illegal activities, stuff they would want to hide from authorities, basically. And more recently, that's also been Russian oil export, because they try to basically hide where they're going, because they still want to sell their oil, despite these sanctions being put against Russia. So that's some of the more relevant stuff in the recent years. But how do we detect these invisible ships? Well, that was basically part of my project. And for that, I used actually 3 methods. That's the multimodal part. I used webcams, satellites, and AIS signals. I'll explain a little bit more about them now. So I used for the webcams, I took publicly available webcams on the internet that broadcast to the internet openly. Yes, you might know this is actually the Great Belt Bridge in Denmark. And I was just comparing the computer vision detections on these images in real time with what I saw from the transponder signals. And if I saw a ship, there was no transponder signal correlated to it, well, that means basically that there's a dark ship passing by. And I did this for multiple cameras around the Baltic Sea. You see here, one of these ships is actually a Danish warship, and these actually do not need to transmit. It's not mandatory for them to transmit their AI signal, but it's still an example of a dark vessel, albeit not illegal. So that was one way I did it. Second way was using satellite images. So this is using radar reflections from the Earth. You can detect these vessels by their, well, pretty bright radar reflection because they're all metal ships and they reflect the signal really, really well. And you can detect these ships using some algorithms in these images. And you can compare them with your AI signals. And any mismatches basically indicate the presence of a dark vessel. And the third method is just by looking at this AI signal alone. Now you might think, if there's none, how do you detect them? Well, you detect them from the point that they disappear, basically. So you track ships, all the ships in an area, and if any disappear or if any anomalies are present, you can think, okay, is this the cause of someone turning off their AIS transponder? And that's what I did with the IIS, among other things. And here's an example that one ship turned off their transponder in the middle of the Baltic Sea. Actually, it's above Nord Stream. That's why it was so important, Nord Stream, the pipeline in the Baltic Sea. And that's how we detect, just by looking at the AIS signals, if there's any anomalies. My thesis here then at ETH, because I guess that's a big part of that. That is my stay here. So you see a little bit in the background, a lot of wind turbines, a lot of wakes that are behind them. And actually, those wakes are the key problem behind my thesis. So wakes in wind farms are the disturbed air left behind by turbines because they extract energy out of the air, which means the wind speed drops behind the turbine. And actually, there's a lot more turbulence behind the turbine as well. And this actually ends up downstream in your downstream turbines, as you can see in this figure, for example. And this actually means that there's power loss and increased loads at these downstream turbines. Lower wind speed means lower energy production, which you want to avoid. And the increased turbulence increases your loads on your downstream turbines, which you also want to avoid. So we can try to mitigate this using something called wave steering, which is turning your turbines with reference to the wind. You can basically steer this wake a little bit. It's not much, but just enough so you can keep your wake out of your downstream turbines. I mean, that works, but there's of course no such thing as free lunch. Your upstream turbines are now misaligned with the wind, and that increases their loads in turn. So you're trying to solve one problem, but you're creating another. And there's some trade-off between power and loads, between your downstream turbines, upstream turbines, and your whole wind farm as a whole, basically. And this trade-off, that's what we want to try to optimize, but especially in the long term. So the actually goal is to maximize this wind farm profit in the long term. And when I'm talking about long-term consequences, I'm talking about mostly the loads, because your power you optimize basically directly. You get directly your reward for some yaw optimization in your wind farm. With your loads, actually those matter in a couple of years because those loads contribute to failure of your components, degradation of your components over time, which is not something that immediately happens in your next few hours or days. So this component degradation, that's the long-term effect. Your short-term powers, your short-term reward, your short-term effect, and this trade-off between them is something that is actually perfect for reinforcement learning to learn. Because if you know anything about reinforcement learning, you hear the words long-term consequences, reward optimization, and decision-making using the wake steering. That screams reinforcement learning. So that's actually what I'm using. So I'm creating this controller basically. And this controller needs an environment to train in. It needs to act in an environment and experience the consequences of its actions and updates its policy basically based on that. So it needs to play around and figure out what's the best way of tackling this problem. And this environment needs to be, well, one, fast. It needs to be realistic. It also needs to model the long-term effects. Those are three things that we really need to have in this environment for this controller to be applicable to real life later on. So to solve the first requirement, we can use a surrogate instead of a full wind farm simulation, which would take too long, which you might need to simulate thousands of time steps pretty quickly, and we cannot do that with a very complicated solver. So some of you will know that Gregory here worked on the GNN, ground neural network surrogate, which imitates a wind farm solver called PyWake, which normally runs in the order of seconds, but now can run in the order of milliseconds. And that's what we need. So it imitates these calculations, but much faster. And it models these power and loads. That's what we need, because that's actually what the results are of your yawing strategy. And the fatigue model I'm using for long-term effects, because these loads on your turbine are mostly cyclic in nature. They're not as big that they destroy your turbine immediately, but they're just enough to degrade your component over time. And for that, I'm using fatigue failure. Some of you will know it from material science. And this models the long-term effects of loads. And the environment basically couples the reinforcement learning with the environment, the simulation, which is the surrogate, GNN surrogate, and all the other components, which basically determine all the long-term and short-term effects. So yeah, I mean, I have to extend the GNN surrogate with yaw angles, because Gregory's one does not currently take into account the yaw angles. These yaw angles, the rotations of the turbines, are actually important for modeling a wind farm, so these need to be integrated into that model. And also the operating modes, which are where a turbine is on or off. If it's off, it doesn't interact with any of the other turbines in the wind farm. If it's on, it does. So that should also be incorporated, because there can be downtime due to maintenance in your environment. And I have to redo the load circuit. So PyWave, which is what the GNN circuit is trained on, it has a load model, but it does not take into account the yaw angles, and it's also not very realistic, not very complicated either, and not very accurate. So I chose to redo this whole load circuit, basically a neural network that can predict the loads based on the local conditions of wind speed and turbulence at a wind turbine. And I ran 18,000 open fast simulations and trained on circuits based on that. So I get a new load estimation, basically, given the wind conditions. And using that data, I can retrain the surrogate and get a better, more accurate surrogate for my environment. And there's an example of the graph of one of the load predictions. And it's interesting to see here that with high turbulence, so in your wakes of the front turbines, as I said, the higher turbulence increases your loads, and we want to avoid this in the environment. This just models it, so we can try to avoid it using our reinforcement learning applications. So yeah, fatigue model for degradation, that's the long-term effects. If you know about fatigue failure, it's the cyclic loads, and these cyclic loads over time create small cracks in your components, and eventually this causes a failure. And I map these cyclic loads to the consumption of a lifetime. So when all the lifetime has been consumed over 6 years of simulation, that's when the component breaks, and at that point there has to be some cost or penalty associated with that, which you have to pay for repair, maintenance, or replacement. And in the end, your reward that your agent experiences, so basically we say, okay, you're doing this good, is dependent on how much power you produce, which maps to electricity and cost, and also your maintenance cost, which is, I guess, a penalty and negative therefore. So your reward is your profit from energy produced minus your cost from maintenance. And see your simple timeline here. You produce your energy, that's your positive reward, your profit. And your negative cost is basically your replacement or repair cost. And I also have to model the downtime, because when a turbine is not working, you're not producing any energy and you're not getting any money from that. So this is what the agent learns as a consequence of its rewards. This is what it gets as a consequence of its actions, I mean. And that's how it learns what is good and what isn't. So yeah, this agent learns the trade-off between this short-term power optimization and also these long-term effects of component degradation and therefore the maintenance that you get. Because you can imagine if you ruin your turbine blades because you're having very high loads, your turbine blades will break down much faster. There's a lot more maintenance in a full turbine lifetime, and even though you get a little bit more power because you do your optimal yaw angles and rotations in your wind farm, you're just paying a lot more for your maintenance, and that's not ideal either. So the result in the end should be profit maximization, and they should outperform the greedy and risk-averse policies. Greedy being just only optimize for power, do not think about loads at all. In the beginning, this might actually get you more power produced because you're more optimal layout of your wind farm, more optimal yaw angles. But in the end, you're paying for that by more maintenance. And the risk averse policy would be to minimize your loads. Okay, be very careful, just get as long as lifetime out of them as possible, but you're not thinking about power at all. And power means money in this case. So you're really slow with getting your profit out of it. And somewhere in between would be the trade-off between getting a lot of power out of your wind farm, but also minimizing the failures of your turbines and minimizing your maintenance costs, basically. So yeah, where am I at with this thesis, the progress so far? So I've created this environment, I've created this degradation model, this fatigue model that maps the loads in the moment to what it means over the long term. I also created some wind sampling, which is just creating wind conditions that are also coherent over time. So you can imagine that the wind comes from that direction, it cannot come from that direction in the next time step. So there's some coherence in this. Also making this look very realistic, because that's also one of the requirements of the environment. Basically to look like real wind inflow conditions. The profit model, also part of it, mapping your power production to how much actually money you get from that. and also the whole backend that basically glues it all together, all these components. Custom load surrogates, I talked about that. That's basically the prediction of your loads based on your local wind conditions. This is important because these loads are actually part of the trade-off, so this needs to be accurately modeled. And I extended the GNN surrogate, Gregory's GNN surrogate, to include the yaw angles in the operating modes. And right now I'm working on retraining this GNN and putting it in the environment so I can actually run this environment over longer time steps, longer periods of time, and basically tune it a little bit such that it's more realistic and eventually implement this reinforcement learning algorithm. And the final figure here is the wind, basically wind conditions that are part of the temporarily coherent wind sampling. So just over time, what does the wind do with wind speed and wind direction? This was interesting as part of the environment. So that's basically my presentation. I hope you learn a little bit more about who I am, what I do, and what I'm doing right now. And if you have any questions, feel free to ask them.